Deep in the rust-coloured landscape of Mars, in a region known as Venodin along the rim of Jezero Crater, something catches the eye. Among the flat, fragmented stones that litter this ancient terrain, one rock stands different. Taller than its neighbours, sculpted by forces unknown, with a surface that bears the unmistakable marks of a violent past. The Perseverance rover pauses, its cameras focusing on this stranger in an alien land. Scientists back on Earth, monitoring the rover's progress from millions of miles away, lean forward in their chairs, because this rock, they will soon discover, doesn't belong here. It never formed on Mars. It came from somewhere else entirely, a visitor from the depths of space, carrying with it secrets from the earliest days of our solar system. This is the story of Phippsaksla, an iron-nickel meteorite discovered in November 2025 that has captured the imagination of planetary scientists around the world. But to understand why this particular rock matters so much, we need to journey back through billions of years of cosmic history, trace the path of this metallic wanderer through the void of space, and understand what its presence on Mars tells us about the violent creative forces that shape the planets we see today. Before we dive in, don't forget to subscribe for more journeys through strange worlds and cosmic relics. So, let the story begin. The discovery came during what might have seemed like a routine day in the Perseverance rover's mission. For more than 4.5 years, this car-sized robotic explorer had been methodically making its way across the Martian surface, studying rocks, drilling samples, and sending back images that have revolutionized our understanding of the Red Planet. By November 2025, Perseverance had already travelled dozens of kilometres, collected numerous samples for future return to Earth, and made discoveries that suggest Mars was once a far more hospitable world than the cold, dry desert we see today. But on this particular sol, as Martian days are called, the rover's instruments detected something unusual. The rock wasn't just sitting on the surface like most of the stones around it. It was perched atop ancient bedrock that scientists knew had been thrust up from deep underground when an asteroid slammed into Mars nearly 4 billion years ago, creating the crater that would later fill with water and sediment to become Jezero. The rock measured roughly 80 centimetres across, about 31 inches, making it roughly the size of a small desk or a large watermelon. But size wasn't what made it interesting. What caught the attention of mission scientists was the rock's appearance. In a landscape dominated by flat, broken fragments of stone, this rock stood tall and proud, its surface bearing a curious sculpted quality, as if it had been carved by an artist's hand. The weathering patterns were unlike anything else in the immediate vicinity. There were cavities and indentations across its surface, features that planetary geologists call regmaglypts, thumbprint-like impressions that form when meteorites burn through planetary atmospheres, their surfaces melting and flowing like candle wax in the intense heat of atmospheric entry. The mission team gave this mysterious visitor a name, Phippsaksla. In the tradition of Perseverance's mission, where features on Mars often receive names from locations on Earth or terms from various cultures, this designation would stick as scientists began their investigation into what this rock truly was and where it had come from. The initial images sent back from Perseverance's Mastcam-Z cameras showed the rock in striking detail. These aren't your ordinary cameras. Mastcam-Z represents a pair of sophisticated imaging systems mounted high on the rover's mast, capable of capturing stereoscopic, high-resolution images in multiple wavelengths of light. They can zoom in on distant features, track the movement of dust devils across the Martian plains, and document the rover's discoveries with remarkable clarity. The images of Phippsaksla revealed a dark grey to black surface, notably different from the reddish-brown basaltic rocks that make up most of the Martian terrain around Jezero Crater. But images alone couldn't tell the full story. To truly understand what they were looking at, the mission team needed to know what this rock was made of. That's where SuperCam came in, one of the most sophisticated instruments ever sent to another planet, and the key to unlocking Phippsaksla's secrets. SuperCam is a marvel of modern engineering, a suite of instruments that can analyse rocks from a distance using techniques that would seem like science fiction just a few decades ago. Mounted on top of Perseverance's mast alongside the cameras, SuperCam can fire lasers at rocks more than 7 meters away and determine their chemical composition by analysing the light that results from these laser strikes. It's a technology called laser-induced breakdown spectroscopy, or LIBS, and it has revolutionised our ability to study other planets without needing to physically touch every single rock we want to investigate. Here's how it works, and it's genuinely remarkable. SuperCam fires a powerful infrared laser pulse, operating at a wavelength of 1064 nanometers at a target rock. The laser pulse is incredibly brief, lasting only a few nanoseconds, but it carries enough energy to heat a tiny spot on the rock's surface to temperatures exceeding 10,000 degrees Celsius in an instant. This extreme, focused heat vaporizes a microscopic amount of the rock material, creating what scientists call a plasma, a state of matter where atoms are stripped of their electrons and begin to glow intensely. This plasma, though it only exists for a fraction of a second, emits light at specific wavelengths that are characteristic of the elements present in the rock. Think of it like a chemical fingerprint written in light. Every element, when heated to these extreme temperatures, produces its own unique pattern of spectral lines. Iron emits light at certain wavelengths, nickel at others, silicon at still others, and so on through the periodic table. SuperCam captures this light using 3 different spectrometers, instruments designed to split the light into its component wavelengths, like a prism splitting sunlight into a rainbow, but with far greater precision and range than any rainbow you've ever seen. When the mission team aimed SuperCam at Phippsaksla and fired the laser, what they saw in the resulting spectrum was extraordinary. The rock showed unusually high concentrations of iron and nickel, elements that on Mars are typically found in much lower abundances and almost never together in such high proportions. The readings were clear and consistent across multiple laser shots, each one vaporizing a tiny additional bit of the rock's surface. This wasn't a fluke or a measurement error. This rock had a chemical composition fundamentally different from native Martian rocks. In all the rocks that Perseverance had analysed in Jezero Crater up to that point, nothing had shown this particular chemical signature. The crater floor itself was made primarily of igneous rocks, stones formed from molten magma, either underground or from volcanic activity at the surface. These rocks contained the minerals you'd expect in a volcanic environment: olivine, pyroxene, plagioclase feldspar. They showed evidence of having interacted with water over the eons, with carbonates and sulfates mixed into their mineral assemblages. But high iron and nickel together? That was new. This combination of elements is the calling card of a specific type of meteorite, one that forms in perhaps the most extreme and ancient environments in our solar system. To understand what Phippsaksla truly is, we need to journey back more than 4.5 billion years to the chaotic early days of our solar system's formation, when the planets were still being assembled from the primordial disk of gas and dust that swirled around our young sun. The story of iron-nickel meteorites begins in fire and pressure, deep within small planets that no longer exist. In the first few million years after our sun ignited, the solar system was a vastly different place than the relatively orderly arrangement of planets we see today. The young sun was surrounded by a massive disk of material, the protoplanetary disk, a swirling cloud of gas, dust and ice that extended billions of kilometers into space. Within this disk, particles began to stick together, growing from dust grains to pebbles to boulders to objects kilometers across. These early planetary building blocks are called planetesimals, and they were the raw material from which all the rocky planets, including Earth and Mars, would eventually be assembled. During this epoch, roughly 4.56 billion years ago, thousands of planetesimals populated the inner solar system, ranging from a few kilometres to hundreds of kilometres in diameter. They collided, merged, broke apart, and gradually grew into larger bodies. But something remarkable happened inside some of these planetesimals, something that would ultimately give rise to meteorites like Phippsaksla. Many of these early bodies contained radioactive elements, particularly a form of aluminum called aluminum-26. This isotope has a relatively short half-life by cosmic standards, only about 700,000 years, which meant it was abundant in the earliest days of the solar system, but quickly decayed away. As it decayed, aluminum-26 released heat, tremendous amounts of heat, enough to melt the interiors of planetesimals that were large enough to retain this thermal energy. When these bodies melted, something extraordinary occurred. Like oil and water that separate when mixed, the molten material inside the planetesimals separated according to density. The rocky silicate minerals, lighter and less dense, rose toward the surface. The metallic elements, primarily iron with significant amounts of nickel and traces of other metals like cobalt, germanium and gallium, sank toward the centre under the pull of gravity. This process, called planetary differentiation, is the same process that gave Earth its iron-nickel core. But these planetesimals underwent this transformation on a much smaller scale and over a much shorter time frame. In the heart of these molten worlds, metallic cores formed, composed primarily of iron with typically 5 to 20% nickel by weight. These cores were entirely liquid initially, great spheres of molten metal floating in mantles of molten rock. But as these small worlds cooled over millions of years, the cores began to solidify from the inside out, cooling at rates of roughly 1 degree Celsius per million years. This incredibly slow cooling rate is key to understanding what makes iron-nickel meteorites so special, and so immediately recognizable. As the molten metal cooled, 2 different iron-nickel alloys crystallized out of the melt at different times and temperatures. The first was camosite, an alloy containing relatively low nickel content, typically around 5 to 7.5%. The second was taenite, a nickel-rich phase that could contain up to 50% nickel. These 2 alloys have different crystal structures, and as they crystallized during the incredibly slow cooling process, they formed intergrown interlocking plates and bands, creating a distinctive geometric pattern. This pattern, called a Widmanstätten pattern, after Count Alois von Beck-Widmanstätten, who first documented it in the early 19th century, is one of the most beautiful and distinctive features visible in iron meteorites. When a slice of an iron meteorite is cut, polished and etched with acid, the acid attacks the camosite and taenite at different rates because of their different nickel content. This differential etching reveals the Widmanstätten pattern, an intricate interlocking lattice of metallic crystals that looks almost like abstract art. The scale of these patterns, whether coarse with bands several millimeters wide or fine with incredibly thin lamellae, tells scientists about the exact cooling rate the meteorite experienced in its parent body's core. These patterns are impossible to create in terrestrial iron or through any human manufacturing process because they require such extraordinarily slow cooling rates. They can only form in the insulated heart of a planetesimal, where the surrounding rock acts as a perfect blanket, allowing the metal to cool at a pace measured in geological time. The presence of a Widmanstätten pattern is therefore proof positive of extraterrestrial origin. It's a signature written in metal that cannot be forged, but these cores were not destined to remain intact forever. The early solar system was a violent place, with objects constantly colliding as they orbited the Sun. Some of these impacts were gentle by cosmic standards, resulting in mergers that built larger bodies, but others were catastrophic, energetic enough to completely shatter planetesimals that had taken millions of years to cool and differentiate. When a planetesimal with a metal core was struck in one of these catastrophic collisions, the impact could strip away the rocky mantle and crust, exposing the core to space and scattering fragments throughout the solar system. These fragments became the iron meteorites we find today on Earth, on the Moon, and as we're now discovering on Mars. Each iron meteorite is a piece of a core from a planetesimal that no longer exists, a remnant of a world that was destroyed billions of years ago in the violent early days of solar system formation. When we hold an iron meteorite in our hands or study one sitting on the surface of Mars, we're looking at material from the interior of a small planet that died before the Earth even finished forming. The chemistry of these iron meteorites tells us even more about their origins. Scientists have identified at least 14 distinct groups of iron meteorites based on their trace element compositions, particularly the ratios of elements like gallium, germanium, and iridium. Each group likely represents the core of a different parent body, a different shattered planetesimal. The largest group, called Tritiab, contains meteorites with a remarkably consistent pattern of elemental abundances that suggest they all crystallized from the same metallic melt as it cooled and solidified in a single parent core. Other groups show more complex histories. Some meteorites don't fit neatly into any group and are classified as ungrouped, suggesting they come from parent bodies that are unique, or for which we simply haven't found enough samples to establish a clear pattern. Recent research has even shown that some iron meteorite groups formed in different reservoirs within the early solar system, with some coming from the inner solar system and others from regions farther out, possibly beyond where Jupiter formed. The isotopic signatures preserved in these ancient metals provide clues about the structure and evolution of the protoplanetary disk itself. Phippsaksla, sitting on the Martian surface, is one of these cosmic wanderers. Based on the preliminary SuperCam analysis showing high iron and nickel content, it's almost certainly an iron meteorite, a fragment of a planetesimal core that formed in the earliest days of the solar system. But how did it end up on Mars? And more intriguingly, why did it take Perseverance more than 4 years to find one when other Mars rovers had encountered these metallic visitors much more quickly? The path from the asteroid belt to the surface of Mars is not a simple one. Iron meteorites don't simply fall straight from the sky like rain. They follow complex orbital paths, their trajectories shaped by gravity, collisions, and the subtle but persistent pressure of sunlight itself. Understanding how Phippsaksla arrived at Jezero Crater requires us to consider the dynamics of the inner solar system and the constant rain of debris that falls on all the terrestrial planets. When a planetesimal is shattered in a collision, the resulting fragments don't all follow the same path. Some pieces might be ejected at high velocities, escaping into orbits that take them throughout the solar system. Others might remain in orbits similar to the parent body, becoming part of the asteroid belt's population. Still others might be nudged into unstable orbits by the gravitational influence of Jupiter, the solar system's massive traffic cop, whose gravity can either protect the inner planets from impacts or funnel objects toward them, depending on the specifics of their orbits. Mars, being closer to the asteroid belt than Earth, receives impacts from space debris more frequently than our home planet does. Scientists estimate that meteorites strike the Martian surface essentially every day, though the vast majority of these are small, ranging from pebbles to perhaps fist-sized rocks. Only about 1 in 20 of these impactors are iron meteorites, the rest being stony meteorites or carbonaceous materials. But over geological time, this steady bombardment adds up, depositing meteoritic material across the entire Martian surface. According to Professor Gareth Collins from Imperial College London, an expert on meteor impacts, Mars gets hit by meteors constantly, with impacts occurring on a daily basis, though the exact number is difficult to pin down precisely. The Martian atmosphere, thin though it is compared to Earth's, still subjects incoming meteorites to significant heating and stress during atmospheric entry. Smaller stones often break up entirely, scattering as meteor showers, but iron meteorites, being both dense and strong, have a much better chance of surviving this fiery descent intact. The resilience of iron meteorites to both atmospheric entry and subsequent weathering on the Martian surface is one reason why they're relatively common finds for Mars rovers, even though they represent only a small fraction of the total meteoritic material falling on the planet. Stony meteorites, made of the same silicate minerals as most Martian rocks, can be nearly impossible to distinguish from native rocks without detailed chemical analysis. But iron meteorites stand out visually, their metallic luster and distinctive shapes making them obvious targets for investigation even from a distance. Dr. Gareth Dorian from the University of Birmingham suggests that Phippsaksla likely originated in the asteroid belt, that region of rocky and metallic debris orbiting between Mars and Jupiter. This belt contains millions of objects, from dust particles to dwarf planets, remnants from the early solar system that never coalesced into a proper planet due to Jupiter's gravitational influence. Many of these objects are fragments from collisions, and among them are pieces of differentiated planetesimals, complete with metallic cores. The journey from the asteroid belt to Mars probably took thousands to millions of years. Phippsaksla would have orbited the Sun in the asteroid belt, perhaps for billions of years, until some perturbation, a collision with another object or a gravitational nudge from Jupiter or Mars itself, changed its orbit just enough to bring it into a trajectory that would eventually intersect with the red planet. When it finally entered Mars' thin atmosphere, travelling at speeds of several kilometres per second, the rock experienced intense heating on its surface. The outer layers melted and flowed, creating those distinctive regmaglypts, those thumbprint-like indentations that first caught Perseverance's attention. Then came the impact. Despite travelling at cosmic velocities, Phippsaksla was small enough and strong enough that it probably didn't create a significant crater on impact. Instead, it likely hit the surface relatively intact, perhaps breaking into a few pieces, and came to rest atop the ancient bedrock where Perseverance would find it millions or perhaps billions of years later. The fact that it sits on top of impact-formed bedrock outside the main crater floor suggests it fell relatively recently in geological terms, after the bedrock was already exposed by erosion and other processes. If it had fallen while Jezero Crater still contained its ancient lake billions of years ago, it would likely have been buried under layers of sediment. What's particularly intriguing about Phippsaksla's discovery is how long it took for Perseverance to find an iron meteorite in Jezero Crater. The Curiosity rover exploring Gale Crater on the other side of Mars has found numerous iron meteorites during its mission, including notable specimens like Lebanon, a massive iron meteorite roughly 1 metre across discovered in 2014, and Cacao, a 30-centimetre specimen found in 2023. The Spirit and Opportunity rovers, which explored Mars in the 2000s and 2010s, also encountered iron meteorites during their missions. Heat Shield Rock, discovered by Opportunity in 2005, was particularly significant as the first meteorite found on another planet. It was sitting on the surface not far from where the rover's heat shield had impacted, creating an odd cosmic coincidence of human-made and natural space debris in close proximity. Given that Jezero Crater is roughly the same age as Gale Crater, both formed around 3.8 to 3.9 billion years ago, and given that orbital observations had revealed numerous small impact craters within Jezero suggesting a long history of meteorite impacts, scientists had expected Perseverance to encounter iron meteorites relatively early in its mission. The fact that it took more than 4.5 years and over 1,600 Martian days for Perseverance to find Phippsaksla suggests either that the rover's path simply hadn't crossed paths with any obvious iron meteorites until now, or that such meteorites are less common in the specific regions Perseverance explored within the crater interior. Now that Perseverance has moved to the crater rim, exploring terrain that was uplifted from deep underground during the impact event, the geological setting has changed dramatically. This bedrock is ancient, dating to Mars' earliest history, and it provides a different environment than the sedimentary deposits and volcanic rocks that dominate the crater floor and delta region. The discovery of Phippsaksla in this new setting opens questions about the distribution of meteorites across different Martian terrains, and how the timing of meteorite falls relates to the geological history of specific locations. To fully appreciate what Perseverance has accomplished in identifying and analysing Phippsaksla, we need to understand the sophisticated suite of instruments that makes the rover so capable. At the heart of this discovery is SuperCam, but SuperCam is just one part of a carefully orchestrated system of sensors and tools that work together to explore Mars in unprecedented detail. SuperCam itself is a marvel of miniaturization and integration. It combines 4 different types of spectroscopy in a single instrument package, each technique providing different information about the rocks and soil it examines. We've already discussed laser-induced breakdown spectroscopy, the LIBS technique that analyzes the plasma created when the laser strikes a rock. But SuperCam can do much more. The instrument also includes a Raman spectrometer, which uses a different laser, this one green with a wavelength of 532 nanometers, to investigate the molecular structure of materials. In Raman spectroscopy, most of the laser light reflects back at the same wavelength, but a tiny fraction interacts with the target's molecules in a way that shifts the wavelength of the returning light. These wavelength shifts are characteristic of specific molecular bonds and mineral structures, allowing scientists to identify not just which elements are present, but how they're arranged in chemical compounds. This is particularly valuable for identifying organic molecules, complex carbon-based compounds that could potentially be signs of past life on Mars. While LIBS can tell you that carbon is present in a rock, Raman spectroscopy can tell you if that carbon is part of an organic molecule, a carbonate mineral or graphite. For a mission focused on finding signs of ancient microbial life, this capability is crucial. SuperCam's infrared spectrometer operates in the near-infrared wavelengths from 1.3 to 2.6 micrometers, a range invisible to human eyes but incredibly informative about the presence of water-bearing minerals, particularly clays. The types and abundances of clay minerals give scientists clues about the nature of water that was present in Mars' past, whether it was fresh or salty, acidic or neutral, ice-cold or warm. These are key questions for understanding how habitable Mars might have been billions of years ago when Jezero Crater was filled with water. To keep the infrared detectors operating optimally, they're cooled by small thermoelectric coolers, maintaining temperatures between -100 and -50 degrees Celsius at all times. Even on Mars, where the average surface temperature is already far below freezing, this additional cooling is necessary to reduce thermal noise and ensure the spectrometer can detect the faint infrared signals from rocks dozens of meters away. SuperCam also includes a high-resolution color camera called the Remote Micro Imager, or RMS, which can capture images of features as small as a grain of rice from more than 7 meters away. These images provide crucial context for the spectroscopic measurements, showing scientists exactly what part of a rock they're analyzing, and revealing details about texture, layering and weathering that aren't visible in lower resolution images. Perhaps most unusually, SuperCam includes a microphone, the first instrument designed to record sound on Mars. This microphone serves multiple purposes beyond just listening to the Martian wind, though those recordings are scientifically valuable for understanding atmospheric turbulence. When SuperCam fires its laser at a rock, the microphone can record the sound of the laser-induced plasma, and the characteristics of this sound provide information about the rock's hardness and whether it has surface coatings. Harder rocks produce different acoustic signatures than softer ones, and this acoustic data complements the spectroscopic information to give a more complete picture of what the rover is examining. All of this technology is packed into a relatively compact package divided into 2 main parts. The mast unit sits atop Perseverance's remote sensing mast, the tall pole, that extends up from the rover's body, giving SuperCam a high vantage point with a clear view of the surrounding terrain. The body unit, containing most of the spectrometers and processing electronics, is housed within the rover's main body, where it's better protected from the harsh Martian environment. The instrument is a joint effort between teams in the United States and France, with contributions from scientists and engineers in Spain, Canada, Denmark, and Germany. It builds on the success of ChemCam, a similar but less capable instrument on the Curiosity rover that has been operating since 2012. SuperCam represents an evolution of that technology, adding Raman and infrared spectroscopy capabilities and improving the quality and range of measurements. When SuperCam examined Phippsaksla, it could work quickly without requiring the rover to drive right up to the rock or position its robotic arm for contact measurements. From several meters away, the instrument fired multiple laser shots at different spots on the rock's surface, each shot vaporizing a microscopic amount of material and providing a measurement of its composition. The laser can also be used to blast away surface dust, giving a clearer view of the solid rock underneath without any need for brushes or other contact tools. The data from these analyses is transmitted back to Earth via the Deep Space Network, NASA's constellation of giant radio antennas spread across the globe. Each day's worth of observations might generate dozens of megabytes of data, including high-resolution images, spectroscopic measurements, and environmental data from the rover's various sensors. Mission scientists review this data and plan the next day's activities, deciding where Perseverance should drive, which rocks to examine in detail, and whether any samples are compelling enough to drill and cache for eventual return to Earth. The identification of Phippsaksla as a likely iron meteorite came from this careful analysis of SuperCam data, with scientists comparing the spectroscopic signatures to their extensive databases of known rock and meteorite compositions. The high iron and nickel content was unmistakable, providing strong evidence for a meteoritic origin even before any other analyses were performed. To understand the full significance of finding Phippsaksla at this particular location, we need to explore the remarkable history of Jezero Crater itself, a history that spans nearly 4 billion years and encompasses dramatic transformations from a cratered wasteland to a lake-filled basin to the dry, wind-swept crater floor we see today. Jezero Crater, whose name comes from the Slavic word for lake, appropriately enough, formed approximately 3.9 billion years ago when a large asteroid or comet slammed into Mars's northern hemisphere. The impact was catastrophic, excavating a bowl-shaped depression roughly 45 kilometers or 28 miles across and throwing up a rim of material that included rocks from deep underground, some of which had never seen the surface before. For perhaps hundreds of millions of years after the impact, Jezero remained a dry crater, one of countless such scars covering Mars' ancient highlands. But then, billions of years ago, when Mars still had a thicker atmosphere and liquid water could exist on its surface, something remarkable happened. Water began to flow into the crater. Orbital observations show clear evidence of ancient river channels carved into the crater's western rim. Channels that would have carried water from the surrounding highlands down into the crater depression. This inflowing water filled Jezero to create a lake that scientists estimate reached up to 22 miles, or 35 kilometers, in diameter, and as deep as 30 meters, or about 100 feet. That might not sound particularly deep by terrestrial standards, but it represents a substantial body of water comparable in surface area to some of Earth's smaller lakes. The water flowing into this lake carried sediment, particles of rock and clay eroded from the surrounding landscape. As rivers enter lakes and their flow velocity decreases, they drop their sediment load, and over time this creates fan-shaped deposits called deltas. The Jezero Delta is particularly well preserved, visible in orbital images as a broad fan of sedimentary material extending into the crater from the river channels that fed it. This delta contains layers of rock, each layer representing a different period in the lake's history, a geological record written in stone. What makes the Jezero Delta especially interesting to astrobiologists is that on Earth, river deltas are excellent at trapping and preserving organic material. When rivers carry water through landscapes, they pick up all manner of material, including any organic compounds present in the environment. As this material settles out in the delta, it can be buried and preserved for billions of years. If Mars ever harboured microbial life, and if that life existed in or near the watershed that drained into Jezero, then the delta sediments are one of the best places in the solar system to look for evidence of it. This is why Jezero was ultimately selected as Perseverance's landing site, after extensive debate and comparison with other candidate locations. The combination of a lake, a delta, and excellent preservation made it an ideal target for a mission whose primary goal is to search for signs of ancient microbial life. The crater also offered practical advantages for landing, with relatively flat terrain in the landing area and fewer large boulders that could pose hazards during the descent. Perseverance landed in Jezero on February 18, 2021, touching down on the crater floor in a region now called Octavia E. Butler Landing, named after the acclaimed science fiction author. From that landing site, the rover began its systematic exploration of Jezero's geology, first examining rocks on the crater floor, then making its way to the delta deposits, and finally, by late 2024 and into 2025, beginning to explore the crater rim itself. The story that Perseverance has uncovered in Jezero is one of dramatic environmental changes over vast stretches of time. The crater floor itself proved to be composed primarily of igneous rocks, stones formed from molten magma, rather than the sedimentary rocks scientists had initially expected. This suggests that after the impact that created Jezero, there was a period of volcanic activity, with lava flows covering parts of the crater floor. These igneous rocks show clear signs of having interacted with water later in Mars' history, with water-bearing minerals like carbonates and sulfates present in the rock matrix. Above these igneous basement rocks, Perseverance found sedimentary layers, including sandstones and mudstones that could only have formed in the presence of liquid water. These rocks record the arrival of the first rivers into Jezero, carrying sediment that would eventually build the delta. The mudstones, in particular, are intriguing because they often contain fine-grained particles that settled out of calm water, the kind of environment where organic material might be preserved if it was present. As Perseverance explored the delta itself, it found boulder conglomerates, rocks made up of rounded stones cemented together, evidence of high-energy flooding events where fast-moving water carried large rocks into the crater. These floods suggest that water flow into Jezero was not constant but episodic, with periods of dramatic flooding interspersed with calmer conditions. This pattern is consistent with a changing Martian climate, perhaps oscillating between wetter and drier periods as the planet's axial tilt varied over millions of years. The rover has collected samples from many of these rock formations, drilling cores about the size of a piece of chalk and storing them in sealed metal tubes. One sample, called Lefroy Bay, contains a large quantity of fine-grained silica, a mineral known on Earth for its excellent preservation of ancient fossils and organic molecules. Another sample location, called Ouzel Falls, contains iron associated with phosphate, a key component of DNA and cell membranes in all Earth life. At Bills Bay, Perseverance found abundant carbonates, minerals that form in watery environments, along with fine-grained silica. These samples are being cached on the Martian surface as part of the Mars Sample Return Campaign, an ambitious multi-mission effort that aims to bring Martian rocks back to Earth for detailed analysis in laboratories far more sophisticated than anything that can be sent to Mars. The goal is to have samples available for scientists to study, with instruments that can definitively determine whether any organic molecules present are biological in origin or formed through non-biological processes. Ground-penetrating radar data from another of Perseverance's instruments, RIMFAX, has confirmed what orbital observations suggested, that Jezero was indeed a long-lived lake with a well-developed delta. The radar can see beneath the Martian surface, revealing the boundaries between different rock layers and showing how sediment accumulated over time. This subsurface view has confirmed that the rocks visible at the surface represent their original depositional environment, not just the conclusion of a long geological story of erosion and redeposition. Eventually the lake dried up. Mars's atmosphere was thinning, perhaps stripped away by the solar wind, after the planet's magnetic field weakened and failed to provide protection. Surface temperatures dropped as the greenhouse effect weakened. Water could no longer remain liquid for long periods. The lake evaporated, the rivers stopped flowing, and Jezero returned to being a dry crater. slowly filling with wind-blown dust and occasionally struck by meteorites from space. By the time Perseverance arrived over 3.5 billion years later, Jezero was a place of profound stillness, its ancient waterways marked only by the rocks they left behind. The crater rim, where Phippsaksla was found, represents some of the oldest accessible terrain on Mars, bedrock that was deep underground when the impact occurred and was thrust up to form the crater's walls. This bedrock dates to Mars' earliest history, the Noachian period, when the planet was young and its geological evolution was just beginning. The discovery of Phippsaksla on this ancient terrain adds another chapter to Jezero's story, a reminder that throughout all these geological eons, Mars continued to be bombarded by material from space. The meteorite is far younger than the bedrock it sits upon, a recent arrival in geological terms, but its presence here connects Jezero not just to Mars' own history, but to the broader story of the solar system. Phippsaksla is not alone in its journey to Mars. In fact, the surface of the red planet is littered with meteorites, visitors from space that have been accumulating for billions of years. The dry conditions on Mars, with no rain to weather rocks away, and no plate tectonics to subduct and recycle surface materials, mean that meteorites can persist on the surface for enormous lengths of time, far longer than they would on Earth. The story of finding meteorites on Mars begins almost as soon as rovers arrived on the planet. The Mars Exploration Rover Opportunity, which operated from 2004 until 2018 in an epic mission that far exceeded its planned 90-day lifespan, made the first confirmed discovery of a meteorite on another planet in January 2005. The meteorite, nicknamed Heat Shield Rock because it was found not far from where Opportunity's heat shield had impacted the surface during landing, was an iron meteorite about the size of a basketball. Initial visual identification was confirmed when Opportunity examined the rock with its alpha particle X-ray spectrometer, which showed the characteristic high iron and nickel content. Heat shield rock set a precedent. If meteorites were sitting on the Martian surface in plain sight, rovers could find them and study them without any special effort. They just needed to keep their cameras open and their science teams alert for unusual rocks that didn't match the local geology. Opportunity went on to find many more meteorites during its 14-year mission. In July 2009, it encountered Block Island, a massive iron meteorite about 60 centimetres across, roughly 2 feet, and estimated to weigh about half a ton. Block Island showed the characteristic weathered appearance of iron meteorites, with deep pits and cavities across its surface. Close-up images revealed patterns on the rock's surface that strongly suggested a Widmanstätten structure, though without cutting and polishing the rock, which obviously wasn't possible, this couldn't be confirmed definitively. Just a few months later, Opportunity found another iron meteorite, this one called Shelter Island, only about 700 metres from where Block Island was discovered. Shelter Island was smaller, about 47 centimetres long, but it showed similar features, suggesting it might even be a fragment of the same original meteorite that broke apart during atmospheric entry. Over at Jezero Crater, Curiosity has been finding meteorites as well. The rover, which landed in 2012 and continues to operate as of 2025, encountered a small iron meteorite called Egg Rock in 2016. About the size of a golf ball, Egg Rock had a distinctive dark grey colour with a submetallic lustre that made it stand out against the surrounding rocks. ChemCam analysis confirmed its meteoritic origin with high iron and nickel content. But Curiosity's most impressive meteorite find came in July 2014 when it encountered Lebanon, a massive iron meteorite roughly 2 metres wide, making it one of the largest meteorites ever found by any Mars rover. Lebanon showed dramatic weathering features, with angular cavities across its surface that might have once been filled with olivine crystals, or represent areas where particularly vulnerable metallic crystals had been preferentially weathered away over the eons the rock sat on Mars's surface. A smaller piece of the same meteorite, called Lebanon B, was found in the foreground. suggesting the meteorite had broken into at least 2 pieces at some point. More recently, in January 2023, Curiosity found another iron meteorite called Cacao, about 30 centimetres across. Cacao was discovered in the sulfate-bearing unit on Mount Sharp, the layered mound Curiosity has been climbing for years. Each of these discoveries adds to our understanding of the meteorite population on Mars and the impact history of the planet. The Spirit rover, Opportunity's twin that operated in Jezero Crater from 2004 to 2010, also found metallic meteorites during its mission. Rocks nicknamed Jong, Shannon Allen Hills, found near Spirit's winter station, were identified as likely iron meteorites based on their spectra. What all these discoveries have in common is that they represent the same type of meteorite, iron meteorites, fragments of ancient planetesimal cores. Stony meteorites, which are far more common in space, are much harder to identify on Mars because they look similar to many native Martian rocks. It takes detailed chemical analysis to distinguish a stony meteorite from a local basalt, whereas iron meteorites stand out visually and compositionally. The frequency with which rovers find iron meteorites on Mars, despite iron meteorites being relatively rare among meteorites in general, tells us something interesting about how meteorites weather on the Martian surface. Iron meteorites are simply more durable than stony ones. They resist weathering and fragmentation better, so they persist on the surface where they can be found by passing rovers. Stony meteorites, by contrast, might break down more quickly or simply be indistinguishable from the rocks around them without close examination. The distribution of meteorites across the Martian surface isn't uniform. Some regions, particularly in the northern lowlands and in areas with old, stable surfaces, have higher densities of meteorites simply because these surfaces have been exposed to space debris for longer periods without being buried by sediment or lava flows. The ancient cratered highlands, where Jezero Crater's rim is located, represent some of the oldest continuously exposed surfaces on Mars, places that have been accumulating meteorites for billions of years. What makes Phippsaksla's discovery particularly significant is the context. While other rovers have found meteorites, Perseverance's discovery comes after the rover has spent years carefully documenting the geological history of Jezero Crater, collecting samples that may contain evidence of ancient life, and building a comprehensive picture of Mars' environmental evolution. The meteorite adds a reminder that throughout all this history Mars has continued to receive visitors from the asteroid belt, each one carrying its own story of formation and destruction in the early solar system. Moreover, Phippsaksla's location on the crater rim, atop ancient impact-formed bedrock, provides opportunities to study how meteorites interact with different Martian terrains, and potentially to understand the timing of meteorite falls relative to the local geological history. Did this meteorite fall recently in geological terms, after the bedrock was exposed by erosion? Or has it been sitting here for hundreds of millions of years, slowly weathering in the thin Martian atmosphere? The discovery of Phippsaksla resonates beyond Mars, connecting to larger questions about the solar system's formation and evolution. Every meteorite we find, whether on Earth, on the Moon, or on Mars, is a sample from the asteroid belt or from other bodies in the solar system delivered to us free of charge by the simple process of orbital mechanics and gravity. These natural samples have been instrumental in our understanding of planetary formation and the early solar system. Iron meteorites in particular have provided crucial insights into how planets differentiate and form cores. By studying the chemistry of different iron meteorite groups, scientists can reconstruct the conditions in their parent body's cores, understanding temperatures, pressures, and the sequence in which different minerals crystallized. This work has shown that the cores of differentiated asteroids underwent processes remarkably similar to what we think occurred in Earth's core, just on a much smaller scale, and with cooling histories we can actually measure through the Widmanstätten patterns. The presence of iron meteorites on Mars also tells us about impact rates and the flux of material throughout the inner solar system. By counting meteorites in different regions and on surfaces of different ages, scientists can estimate how frequently Mars is struck by material from space and how this impact rate has changed over time. This information is crucial for understanding Mars' surface evolution and for planning future human missions, which will need to account for the risk posed by meteorite impacts, small though that risk may be. The chemical and isotopic composition of meteorites has also revealed profound truths about the structure of the early solar system. As mentioned earlier, meteorites fall into two broad categories based on their isotopic signatures: carbonaceous types, which formed in the outer solar system, and non-carbonaceous types, which formed in the inner solar system. The boundary between these two reservoirs is thought to have been created by Jupiter's formation, which occurred early enough that it could influence where different types of material accumulated in the protoplanetary disk. Iron meteorites from both reservoirs show systematic differences in their compositions, with carbonaceous iron cores crystallizing in more oxidized environments and containing different abundances of various trace elements compared to non-carbonaceous iron cores. These differences tell us about the varying conditions in different parts of the early solar system and how planet formation proceeded in regions near and far from the growing gas giant planets. For Mars specifically, the study of meteorites found on its surface complements the analysis of Martian meteorites found on Earth. Yes, we have rocks from Mars here on Earth, ejected from the Martian surface by large impacts and eventually falling to Earth as meteorites themselves. These Martian meteorites, numbering in the hundreds, have taught us much about Mars' internal structure and geological history. But meteorites found on Mars tell a different story, one about the environment that Mars has experienced and the constant cosmic bombardment that all planets endure. The discovery of Phippsaksla also raises practical considerations for Mars exploration. As NASA and other space agencies plan future missions to Mars, including eventual human expeditions, understanding the meteorite population becomes relevant for resource utilization. Iron meteorites are essentially refined metal, potentially useful as raw material for manufacturing if humans establish a presence on Mars. While no one is suggesting we should mine Phippsaksla specifically, the presence of iron meteorites scattered across the Martian surface represents a potential resource that future colonists might utilize. More immediately, the study of meteorites on Mars contributes to our ability to interpret similar objects found in other environments. The Moon, for instance, also has meteorites sitting on its surface, and future lunar exploration missions will undoubtedly encounter them. Understanding how meteorites weather in different planetary environments, how they can be identified remotely, and what they tell us about a planet's history prepares us for exploration elsewhere in the solar system. Phippsaksla will likely remain where it sits for millions of years to come unless future missions decide it's worth collecting. There are no current plans to retrieve this specific rock, though if the Mars sample return mission succeeds in bringing back the samples Perseverance has cached, future missions might consider collecting other interesting specimens, including meteorites. Having an actual piece of an iron meteorite from Mars, which itself is a piece of a destroyed planetesimal from the asteroid belt studied in terrestrial laboratories, would provide opportunities for analysis that aren't possible with remote sensing instruments, no matter how sophisticated. In the meantime, Phippsaksla stands as a monument to the interconnectedness of the solar system, a reminder that we live not on isolated worlds, but in a vast dynamic system where material flows between bodies over geological time. The rock sitting on Mars's surface today might have spent 4 billion years in the asteroid belt before making its final journey to Jezero Crater. In a sense, it's a traveller like Perseverance itself, though its journey took far longer and covered far greater distances. As Perseverance continues its mission in the coming years, the discovery of Phippsaksla marks a milestone but not an ending. The rover has much more terrain to explore around Jezero Crater's rim, regions that promise to reveal even more about Mars' ancient history. The rocks here are among the oldest the mission will encounter, dating back to the Noachian period when Mars still had substantial water on its surface, and a thicker atmosphere that might have kept the planet's surface habitable. The science team will continue to monitor for additional meteorites as Perseverance drives to new locations. Now that the rover has moved beyond the crater floor and delta, it's exploring terrains that have been exposed for billions of years, surfaces that have had ample time to accumulate whatever falls from the sky. It's quite possible that Phippsaksla won't be the only meteorite Perseverance finds in this phase of its mission. Each discovery, whether of meteorites or native Martian rocks, feeds into the larger narrative that Perseverance is constructing about Mars' past. The mission's ultimate goal remains the search for signs of ancient microbial life, but that search requires understanding the full environmental context in which any such life would have existed. The rocks tell stories of water flowing, lakes filling and evaporating, volcanic activity, sediment deposition, and chemical weathering. The meteorites add chapters about cosmic bombardment and the delivery of material from elsewhere in the solar system. The samples Perseverance has collected represent the most carefully selected and scientifically valuable rocks humans have ever chosen from another planet. When these samples eventually return to Earth, if the Mars Sample Return mission overcomes its current budget and technical challenges, they will be studied with instruments far more powerful and precise than anything we can send to Mars. Mass spectrometers that can detect individual atoms, electron microscopes that can image at molecular scales, isotope analyzers that can measure minute variations in atomic masses, all will be trained on these precious specimens. Scientists are particularly interested in the samples that contain fine-grained silica and other minerals known to preserve organic material on Earth. If there are any biosignatures in these rocks, any chemical or structural evidence that life once existed on Mars, these intensive analyses will find them. The results will likely take years to fully understand, as researchers work to rule out non-biological explanations for any potentially interesting organic molecules or structures they find. The implications of discovering definitive evidence of past life on Mars would be profound, forcing us to reconsider our place in the universe and suggesting that life might be common wherever conditions are suitable. Even if no evidence of life is found, the samples will still revolutionize our understanding of Mars' geological evolution and provide constraints on the conditions that existed in the early solar system. Meanwhile, other missions continue to build our knowledge of Mars. The Curiosity rover keeps climbing Mount Sharp, studying layers of rock that record different periods in Mars' history. Orbital missions like the Mars Reconnaissance Orbiter, MAVEN, and the European Space Agency's Mars Express and ExoMars Trace Gas Orbiter provide global context and identify new targets for future exploration. China's Zhurong rover, though currently in hibernation, added new observations from the Utopia Planitia region. NASA's InSight lander, which operated from 2018 to 2022, gave us our first detailed look at Mars' interior, structure through seismology. Future missions are already in planning. The European Space Agency's Rosalind Franklin rover, part of the ExoMars program, is eventually intended to explore Mars with a drill capable of reaching 2 meters below the surface, far deeper than Perseverance's drill can reach, potentially accessing material that has been protected from radiation and oxidation. NASA and ESA are working on the Mars Sample Return architecture, though the exact implementation continues to evolve as both agencies grapple with budget constraints and technical challenges. There's also serious planning underway for eventual human missions to Mars, though these remain at least a decade away and possibly longer. When humans eventually reach Mars, they'll bring capabilities that robotic missions simply cannot match. The ability to traverse great distances quickly, to make rapid decisions about what to investigate, to use complex equipment and conduct extensive field work. But they'll also benefit enormously from the groundwork laid by Perseverance and its robotic predecessors, which will have mapped safe landing sites, identified resources, demonstrated technologies, and revealed the places most worth studying in detail. Phippsaksla, in its own quiet way, contributes to this larger endeavour. It reminds us that Mars is not a static, dead world, but a planet with a complex history that continues to unfold. Material still arrives from space, even if much more slowly than in the solar system's youth. The thin atmosphere still sculpts the rocks, grain by grain. Seasonal cycles of carbon dioxide frost advance and retreat from the poles. Dust devils dance across the plains. Beneath the surface, possibly, liquid water still flows in aquifers deep underground, though we haven't yet confirmed this. Every rock Perseverance examines, every sample it collects, every meteorite it discovers adds detail to our picture of Mars. We're learning to read the planet's geological language, to interpret the stories written in its stones. Phippsaksla's story is one of formation in fire billions of years ago, a journey through space that might have lasted eons, and a final arrival on a world that was once lush with water, but is now desiccated and cold. It's a story that parallels humanity's own journey into the cosmos, our long-held dreams of reaching other worlds finally becoming reality in our lifetimes. Standing back from the technical details and scientific measurements, there's something profound about the very existence of Phippsaksla on Mars. This rock is a physical connection between worlds, a tangible link in a cosmic chain that stretches from the earliest days of the solar system to the present moment. When we look at images of this meteorite sitting on the Martian surface, transmitted across millions of kilometers of space to our screens here on Earth, we're seeing evidence of the deep interconnections that bind the solar system together. The iron in Phippsaksla crystallized in the core of a planetesimal that formed over 4.5 billion years ago, before Earth had fully assembled from its own cloud of planetesimals, before the Moon formed in its giant impact, before life began in Earth's oceans. That planetesimal existed for millions of years as a complete world, a small body with its own internal structure, perhaps its own magnetic field, certainly its own history of impacts and accretion. Then came the catastrophic collision that destroyed it, scattering its remains throughout the inner solar system. For perhaps billions of years, the fragment that would become Phippsaksla orbited the Sun as part of the asteroid belt's population, one object among millions. It witnessed from afar the transformation of Mars from a warmer, wetter world to the cold desert it is today. It was there when Mars's magnetic field shut down, when its atmosphere began leaking away into space, when the last liquid water on the surface froze or evaporated. It was there through all of Earth's history, from the earliest microbes to the dinosaurs to the rise of human civilization. Then, at some point in the relatively recent past, its orbit changed. Perhaps another asteroid bumped it, or Jupiter's gravity tugged it into a slightly different path, or the subtle pressure of sunlight itself, acting over millennia, nudged its trajectory just enough. Whatever the cause, its orbit began to intersect with Mars' path around the Sun, and eventually, inevitably, the two bodies met. The impact would have been dramatic even if it created no significant crater. Travelling at several kilometres per second, Phippsaksla slammed into the Martian atmosphere, its surface heating to thousands of degrees in seconds. The outer layers melted and flowed, creating those distinctive thumbprint textures. Then it struck the surface, probably bouncing or rolling before coming to rest atop the ancient bedrock that now forms Jezero Crater's rim. There it sat, possibly for millions of years, slowly weathering in the thin Martian atmosphere. Dust storms buried and uncovered it. The temperature cycled from bitter cold at night to merely cold during the day. Martian seasons came and went, each one marked by subtle shifts in atmospheric pressure and temperature as carbon dioxide condensed at one pole and sublimated at the other. The rock endured, chemically stable, mechanically strong, waiting. And then, more than 4 billion years after it first formed in a planetesimal's core, and years or centuries or millennia after it landed on Mars, a rover from Earth drove by and noticed it. Cameras captured its image. A laser fired, vaporizing a tiny amount of its surface. Spectrometers analyzed the plasma's light. Data was encoded into radio waves and transmitted to Earth. Scientists on another planet studied the composition of this fragment of a destroyed world. This is not just science. This is humanity reaching out to touch the distant past using technology to extend our senses across the solar system, learning to read the history written in rocks scattered across other worlds. The journey from planetesimal core to rover examination spans most of solar system history and involves 3 worlds: the asteroid where Phippsaksla formed, Mars where it landed, and Earth, whose inhabitants sent a robot to study it. In a very real sense, Phippsaksla connects us to the earliest days of planetary formation. The processes that created it, planetary differentiation through radioactive heating and gravitational separation, are the same processes that gave Earth its iron core. The planetesimals that accreted to form Earth were similar to the planetesimal that gave birth to Phippsaksla, and many of them probably also differentiated before being incorporated into our growing planet. Earth's core might well contain material from dozens or hundreds of destroyed planetesimals, mixed together in our planet's molten heart. The difference is that on Earth, that primordial material has been thoroughly processed by 4.5 billion years of geological activity. It's been melted, mixed, convected, and completely reworked. But Phippsaksla, protected by the vacuum of space and then preserved on Mars' relatively inactive surface, remains largely unchanged from its formation. It's a time capsule, a piece of the earliest solar system delivered to a place where we can study it. This is why Mars exploration matters beyond the search for life, important though that quest is. Mars itself is a time capsule, a world where ancient surfaces remain exposed and accessible, where processes that were erased on Earth by plate tectonics and erosion have been preserved in the geological record. Every rock Perseverance studies, whether it's a Martian stone or a meteorite from the asteroid belt, teaches us something about planetary processes and solar system history that we couldn't learn on Earth because Earth has covered its tracks too thoroughly. The universe is vast beyond human comprehension, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, many of them with their own planets. But right now, in this moment of history, we have exactly one planet we can study in detail from its surface, Earth. And we have exactly one other planet where we have mobile robots capable of exploring and analysing rocks, Mars. Perseverance, crawling across Jezero Crater at a pace measured in meters per hour, represents the cutting edge of our ability to explore other worlds. When future generations look back at this era, they may well mark it as the beginning of humanity's expansion beyond Earth, the period when we first started seriously exploring other planets, when we first started thinking about becoming a multi-planet species. The discovery of rocks like Phippsaksla will be remembered not as isolated findings, but as part of the larger story of how we learn to read the history of worlds. As I write these words, Perseverance continues its journey across Mars. The rover has been operating for more than 1,600 Martian days, far exceeding its planned primary mission duration, with no signs of stopping. Its nuclear power source, a radioisotope thermoelectric generator that converts heat from decaying plutonium-238 into electricity, will continue to provide power for years or even decades to come. Barring catastrophic failure, Perseverance could operate well into the 2030s. During that time, it will continue to explore Jezero Crater's surroundings, studying rocks, collecting samples, and documenting Mars geology in unprecedented detail. It may find more meteorites, adding to our catalogue of these cosmic visitors. It may discover more compelling evidence for ancient habitable environments, perhaps even finding that elusive biosignature that would confirm Mars once harboured life. Or it may confirm through exhaustive study that Jezero, despite its ancient lake and delta and all the ingredients necessary for life, remained sterile. Whatever it discovers, Perseverance's observations will shape Mars exploration for decades to come. The samples it has collected will eventually, we hope, return to Earth where they can be studied with techniques not yet invented, answering questions we haven't yet thought to ask. Future missions will build on Perseverance's findings, targeting locations and phenomena that the rover has identified as particularly interesting. The helicopter Ingenuity, which accompanied Perseverance to Mars and successfully demonstrated powered flight in the thin Martian atmosphere, has shown that aerial exploration of Mars is not only possible, but potentially revolutionary. Future missions may include more sophisticated helicopters, or even fixed-wing aircraft capable of covering vast distances and reaching locations rovers cannot access. These aerial vehicles will be able to quickly scout for interesting rocks, including meteorites, that ground vehicles can then study in detail. Human explorers, when they eventually reach Mars, will have capabilities that far exceed anything robots can do. They'll be able to cover in days distances that take rovers months to traverse. They'll be able to make snap decisions about what to investigate, to recognize subtle features that might elude programmed algorithms, to conduct field geology with the intuition that comes from human pattern recognition and experience. But they'll stand on the shoulders of missions like Perseverance, which will have spent years preparing the way. Phippsaksla will likely still be sitting on Jezero Crater's rim when humans first walk on Mars, unless some future mission decides to collect it. Perhaps one day, decades from now, a human geologist will stand next to this meteorite, running gloved hands over its weathered surface, marvelling that this piece of an ancient destroyed world has now been visited by representatives from the youngest world in the solar system to develop life, intelligence, and spaceflight. That geologist might collect a sample of Phippsaksla to bring back to a growing Mars base, where it could be studied with portable instruments far more capable than anything Perseverance carries. Or perhaps Phippsaksla will remain untouched, a monument to the era of robotic exploration, preserved as an example of the kind of discoveries that early Mars missions made. Future Mars residents might make pilgrimages to see famous rocks, the way we now visit famous geological features on Earth. Phippsaksla, the first iron meteorite found by Perseverance, might become one such landmark. These speculations are flights of fancy, of course. The reality is that Mars exploration remains challenging, expensive, and uncertain. Missions get delayed or cancelled. Budgets fluctuate. Technology sometimes fails. The Mars sample return mission that is supposed to bring Perseverance's samples to Earth has faced severe cost overruns and technical challenges, and its future is uncertain. Human missions to Mars remain aspirational rather than funded programs with firm timelines. But even acknowledging these uncertainties, the trajectory is clear. Humanity is slowly, methodically, building the capabilities to explore and eventually settle on other worlds. Every mission to Mars, whether it succeeds completely or partially or fails, teaches us something valuable. Every rover that operates beyond its planned lifetime, every helicopter that flies in an alien atmosphere, every sample that gets collected, every meteorite that gets identified, adds to our knowledge and capabilities. Phippsaksla, this visitor from the asteroid belt, this fragment of a world that died before Earth fully formed, sits at the intersection of multiple stories. The story of planetary formation, the story of Mars's geological evolution, the story of meteorite science, and the story of human exploration beyond Earth. It reminds us that rocks are not just inert objects, but repositories of history. That careful study of even a single stone can reveal processes operating over billions of years and millions of kilometers. The next time you look up at the night sky and see Mars, that reddish point of light that has fascinated humans since prehistory, remember that there on its surface, in a crater named for a lake, sits a rock from somewhere else. A sample of the asteroid belt delivered free of charge by the simple mechanics of gravity and orbital dynamics. And remember that we've sent a robot there to study it, that humans on Earth can command instruments on Mars to analyze rocks and send back data that teaches us about the origins of worlds. We live in an age of wonders, an age when spacecraft explore the outer solar system, when telescopes peer back to nearly the beginning of time, when rovers on Mars can find meteorites from the asteroid belt and tell us their composition from millions of miles away. The discovery of Phippsaksla is a small wonder in the grand scheme of things, one rock among billions scattered across Mars' surface. But it's our rock, in the sense that we found it, studied it, and are beginning to understand its story. And through understanding this one rock, we understand a little more about the solar system we live in, the processes that shaped it, and our place in the larger cosmic story. So there you have it, the story of a rock that shouldn't be on Mars but is. Phippsaksla started its journey in the heart of a small planet billions of years ago, survived the destruction of that world, spent eons in the asteroid belt, and finally came to rest on another planet, where a robot from yet another planet found it and revealed its secrets. It's a cosmic journey that spans the entire history of the solar system, and we're privileged to be able to read this story through the application of science and technology. The discovery highlights both how far we've come in planetary exploration and how much we still have to learn. We can send sophisticated instruments to Mars and analyse rocks in detail from millions of miles away, but we still can't say with certainty exactly when Phippsaksla arrived on Mars or precisely which asteroid it came from. We can measure its iron and nickel content with impressive precision, but we can't yet bring it back to Earth to study its Widmanstätten patterns or determine its exact crystallographic structure. These limitations are temporary. Technology advances. Missions become more capable. Eventually we'll have the tools to answer all these questions and many more we haven't yet thought to ask. The samples. Perseverance's collecting are a down payment on that future, a set of questions we're saving to answer when we have better tools. In the meantime, Phippsaksla sits on Mars, quietly weathering under the thin atmosphere and the distant sun, a reminder that the solar system is a dynamic, interconnected place where material flows between worlds and where every planet tells stories about the others if we learn to listen. It's a reminder that science is not just about accumulating facts, but about reading history written in nature, understanding processes that operate on scales of space and time that dwarf human experience, and piecing together narratives that span billions of years. The discovery of this single meteorite won't change the world. It won't make headlines for more than a few days, but it represents something important. The ongoing project of understanding our cosmic neighbourhood, of learning how planets form and evolve, of discovering what Mars was like in its youth, and what it might teach us about our own planet's past and future. Every rock studied, every sample collected, every meteorite identified adds another piece to this vast puzzle. And so Perseverance continues its mission, driving across ancient terrain, examining rocks both native and alien, slowly but surely expanding our understanding of Mars. The rover will eventually fall silent, its mission complete, but the data it has gathered will be studied for generations, and somewhere in that data archive will be the detailed measurements of Phippsaksla, a rock that came from somewhere else, a traveller like the rover itself, both visitors to a world that offers endless opportunities for discovery. If you've enjoyed this exploration of Phippsaksla and the science behind its discovery, please consider subscribing to this channel and giving this video a like. We're here to make science accessible, to tell the stories hidden in rocks and stars and planets, to help everyone understand the amazing universe we're lucky enough to inhabit. There's always more to discover, always more stories to tell, always more wonders to explore. Join us for the next one, and together we'll keep learning about this remarkable cosmos we call home. Until next time, keep looking up, keep asking questions, and keep marvelling at the incredible story written in the rocks beneath our feet and the stones scattered across other worlds. The universe is full of mysteries, and every discovery, no matter how small, brings us one step closer to understanding our place in it all.